we are going to go over these questions in the packet. The first one is talking about a goalkeeper in Major League Soccer, and I keep in mind this is from 2009, right? So when I first started using this problem, it was only 2012, and so now it's 2021. So it's a little outdated, but it'll still be appropriate for a binomial model. It says that this goalkeeper saved 67.6% of the shots on his goal in the regular season. Okay, in the playoffs, 21 shots were taken on his goal. So part A just says to explain how this is a Bernoulli trial. So there's three things to make sure this is a Bernoulli trial. The first thing, it's going to be hard to do this if you can't write it. There we go. First time doing this. Okay, the first thing, all right, is to make sure that you have only two options. All right, so we say success or failure. So success or failure. Okay, so what do you guys think? Is this showing a success or a failure? How would you describe a success in this problem? Save the shot. Very good. Right, so success is saved it. Yay! All right, because this is from the goalkeeper's perspective, right? So a success is keeping the ball out of the net, and then a failure then would be they scored, right? So no save made. All right, they scored. All right, so that's the only options we have. Either Nick saved the shot or he did not. All right, the second thing. All right, the second thing is a constant probability of success. So basically, I'm just asking you to tell me, what is our letter P? What is the probability that Nick will save a shot on his goal? What is the probability that Nick saves a shot when it comes at him and he's playing goalie? Very good. So it's 67.6%. So I'm going to write 0.676. So that's what we're going to use as our constant probability of success. That's the second thing. The third thing is independent trials. All right, so to ask yourself, all right, we're talking about the playoffs, so this is probably multiple games. We're talking about 21 shots, different players attempting the shots on Nick. All right, think of game one, the guy kicks the ball, takes a shot. Game two, another guy takes a shot. Is there anything going on that would cause you to believe that each shot is not independent? You know, I mean, maybe, right, if you have the same person taking multiple shots, or let's say, you know, one of the players is like the best player taking a shot, and so their rate of scoring is much higher. I don't have that information, right? So for this problem, I'm going to assume independence. I'm going to assume that if someone takes a shot on his goal, it's not going to affect the likelihood of the next player and their ability to score on Nick. Okay, so I'm just going to assume that because I just don't have enough info. Any questions on these three things? So success or failure, constant probability of success, independent trials. Those are the three things for it to be a Bernoulli trial. That's kind of like the first check. Once you decide it's Bernoulli, then we can go into those options, which is geometric or binomial, right? Remember, geometric from Tuesday is you're waiting until the first success. And binomial is you have a set number of successes out of a total number of trials. So let's look at letter B. Out of 21 shots that he faced in the playoffs, what is the probability that he saves 18? So what model am I going to use for letter B? Is this waiting until he makes the first save? Or is this a number of saves out of a total number of shots? Great, so that's going to be binomial. And hopefully it's a little bit of a giveaway because what's the title of this paper? Binomial distribution. All right? But I still want you to think in that process of waiting or with binomial. Okay, so if I'm going to write down my work, we have the probability that Nick saves 18 shots. All right, I'm going to leave a little blank here. Leave a little blank, come back to it. So let's first talk about his probability of success. So put 0.676. How many saves did he make? No, how many saves did he make? 18, very good. Okay, now, do you know what the probability of failure is? Remember how to find that if you're given the probability of success? All right, looks like Hannah's going to. Hannah, do you remember how to do it? Very good. You subtract it from 1, right? Because it's only a success or failure are the options. So what's going to be our probability of failure? What is it? Excellent. Okay, so 0.324. So Axel, if Nick saves 18 of the 21 shots, how many did he not save? 3. Very good. Okay? Now, if you remember from Tuesday, I'm leaving this blank because there are a number of ways that we can have 18 saves out of 21 shots, right? It could be the first 18, the last 18. You know, the goals could be anywhere in those 21. So what we do, right, if you want to do the actual math, is you do 21 shots, choose 18 are saved. All right, you don't have to do this work. I'm not expecting it. All right, so I'm going to put 21 factorial over 18 factorial times 21 minus 18 factorial. So that's 21 factorial over 18 factorial times 3 factorial. So you have a calculator that can do all that. You also have a calculator. I showed you guys on Tuesday how if you type in 21 and then hit PRB and use the one that says, I think it's NCR. I'd have to check again. And then put 18, it'll give you the answer. All right, and I can do a little bit of math here. 18 factorial is going to cross out with 18 on the top. So I'm going to have 21 times 20 times 19 over 3 times 2 times 1. So really I'm asking what this is. Let's see if I can do a little math here. So that's going to be 7 times 10 times 19. It's going to really test my brain here. So that's 70 times 19. 17 times 20 is 1,400. Take away 70, 1,400 minus 70 is 1,330? Is it 1,330? Yes! All right. So 1,330. So there are 1,330 different ways that you could have those 3 goals that he allowed in the 21 total shots. Okay? So if you went ahead and typed that in, you would get your answer. So what is going to be the likelihood that Nick makes 18 saves out of these 21 shots? I guess while you guys do that, I'll go ahead and go to Desmos so we can confirm that we got the same stuff. All right, so I'm going to go to Desmos binomial distribution. We had 21, move this out of the way, 21 total shots. The probability of Nick making a save was 0.676. And how many did he save? We're saying 18. So did you guys get, oh no, does it not show up? Did you guys get 0.039? Yes? Awesome. 0.039. Now, if you guys saw when I was doing decimals, I'll bring that back up for you. You'll notice that the table, if you've got more than 10 trials, I had to type in that 18 to get the answer. So if you're using decimals, which I highly encourage you to use this to help, just make sure you're like, oh, it's not on the table. Just type in the number you want in X, and that should help. Okay? Now, let's do the next one. The next one says, out of the 21 shots he faced in the playoffs, what is the probability that he saves at least 18? So they've done pretty much the same problem, right? It's still binomial, but now when we use that at least, we're saying what's the likelihood that he saves 18 out of 21, or 19 out of 21, or 20 out of 21, or all 21. So to do this problem the long way, you would do what we did in part B, but for 19, for 20, and 21, and then add up those probabilities. But let's not do that, right? Let's be efficient, and let's just use Desmos, because it will tell us, it'll basically do all the work and add those together for us. All right, so this time, I am going to, sorry about that. There we go. I'm going to tell Desmos that I don't just want 18 out of 21. I want 18, 19, 20, and 21 out of 21. So this upper will now give me my answer, which is 0.055. So when you guys take the test next week, I'm going to allow you to have your Chromebooks with you and the yellow calculators. All right, so you can use Desmos if you need it. Okay? Any questions on A, B, and C? Yes, ma'am. This one, good. So do you remember how we said up here the probability of success is 0.676? So to find Q, which is the probability that he doesn't make the save, you do 1 minus 0.676, which Hannah told me, trusting Hannah here, is 0.324. All right, and that only works, Yasmin, because it's Bernoulli trials, which means you have two options, success or failure. So if you know one of them, you can find the other, because they have to add up to 1. All right, let's go to number 2. Now, number 2 is a completely different problem, all right? And it's a multiple choice question. We have the yearly mortality rate for American men from prostate cancer has been constant for decades at about 25 of every 100,000 men. So 25 out of 100,000 men. What is that as a decimal? What is 25 out of 100,000? All right, Hannah, I think you got it. Point. So 3 zeros after the decimal point? All right, excellent. Now, this is going to sound weird, and I'm not trying to make light of this, all right, but it's going to sound weird. A success in this problem is a man dying of prostate cancer. All right, make sure you understand, I'm not saying that's a success. I'm saying in this problem, a success is that happening, okay? So I need to find the probability that at least one will die from cancer if we're talking about 100 men, okay? So I'm going to do our x is greater than or equal to 1. So I'm going to use Desmos to help me. Whenever I see those two words, at least, I know that I'm going to be going to this calculator. All right, so let's have Juliana. How many total men were in this group? Very good, 100. Nice work. Juliana, what am I going to put for my probability of success? Keeping in mind it's not actually a success. No, what did we say was our P, our probability that a man will die of prostate cancer? Out of 100,000, right? Do you remember what we wrote down for the probability or the decimal? Very good. So 0.00025. Okay? Now we're saying at least 1. Okay, so at least 1. So my lower needs to be 1, and my upper goes all the way to the largest number, which is 100, right? Because it's 100 men. So right here is the answer. 0.025. 0.025. Okay, so I would put C, but you guys see letter B? 0.0247. If you go back to Desmos, you actually see the answer is 0.0247. So some students have been putting B. That's fine as well. Okay. I've been having you guys round pretty consistently to the thousands place. 10, 20, yep. So I would accept both of these. Everybody good? Any questions on this one? Really just as a practice on using the calculator. All right, so what I want you to do is to flip over. We got one more kind of example, and it's about the greatest LeBron James. Now, usually I get some kind of pushback on that, but maybe not this year. Okay. Again, I apologize for how far in the past this was, but it'll work. So we have, in the regular season of 2007-2008, LeBron James made 31.5% of his three-point attempts. It actually gives us his shots made out of his shots attempt. All right, so 113 over 359. During the playoffs that year, LeBron shot 70 three-pointers. So let's see if we can make this Bernoulli. All right, what's the first thing I have to check? Very good. So success or failure. Okay, what is a success? What is a success in this one? Very good. Made the three-pointer. Okay, so then Axel, what's a failure? He misses. Okay. So that's what we have going on. Those are the only two options. Constant probability of success. All right, so what is his probability of success? What am I going to use for letter P? Very good. 0.315 is exactly right. And finally, independent trials. So I'm saying if he shoots a three-pointer, and whether he makes it or misses it, is that going to affect if he makes or misses the next one? They've actually proven this, right? Because if you've ever played a sport like basketball, they have something that's called the hot hand, right? Oh, that guy's feeling it, so give him the ball. That guy's feeling it, right? They've actually done studies on that. It's actually not a thing, right? If you have LeBron's likelihood of making a three for an entire season, whether he's made 2 in a row, missed 3 in a row, made 6 in a row, whatever, the likelihood of him making the next one, you guessed it, is that number. Okay? So this has been proven that taking three-pointers throughout a game are independent trials. Okay, so let's move into letter B. We're going to find the expected number of three-pointers that LeBron is going to make during the playoffs. All right? So we're going to use for expected number, that just means to find the mean. And the formula for the mean is N times P. All right, so how many shots did LeBron take in the playoffs? How many three-pointers did LeBron shoot in the playoffs? What does it say? Say it again? 300. That's how many he took in the playoffs. How many did he take in the playoffs? He took 70, right? So they're getting his rate from the regular season. So 70. We're saying we think he's going to make 31.5% of those. So multiply by 0.315. So how many three-pointers are we expecting LeBron to make in the playoffs that year? $22.05? You get the same thing, Axel? Okay. So we're expecting LeBron to make about 22 of those 70. All right. Let's go to letter C, the standard deviation. All right, so standard deviation, the formula we've used is sigma equals the square root of n times p times q. So let's write those in. We already know n is 70. P is 0.315. And then Yasmin, this is kind of going with the question you asked before. So Q is going to be 1 minus 0.315. So that's going to be 0. Let's see if I can do this. 6, I believe it's 85. All right, so in your calculator, do the square root of 70 times 0.315 times 0.685. Okay, do the square root of that. So it's second. Oh, man. Oh, you got it. Oh, no. Okay. Did you get it, Hannah? 3.88. Yes, so 3.89. 3.89. All right. Everybody doing okay? Because we have one more thing to do. And this is going to be similar to the last thing that we did on Tuesday. All right, so on Tuesday, we went over our two different models, the geometric model, which is weighting, binomial model, which is the number of successes out of a total number of trials. We've been practicing that a lot today. And the last thing I went over on Tuesday was going from the binomial model, which is right now, to the normal model. Do you remember what we have to do to make sure we can use the normal model? What's the one thing we have to check? Very good, Yasmin. We need to make sure that we are expecting at least 10 successes and at least 10 failures. I guess I should say 10 or more, because 10's okay. So 10 or more. So let's do successes. We already did this. Okay? We had n times p, which was 70 times 0.315. You guys told me it was 22.05. So that's 10 or higher. So let's do failures. Failures is n times q. So 70 times 0.685, which is going to be, so I can do this, 47.95, I think. I think that's right. Someone confirm for me that's right. Yeah, okay, cool. Now, what you should notice is that both of those numbers are 10 or higher, okay? So because those numbers are 10 or higher, I'm going to use the normal model, okay? So I'm going to do a little work down here. I'm going to draw a curve. All right, and right in the middle is the mean of 22.05. And with the normal model, I've only ever cared about going 3 standard deviations above and 3 standard deviations below. So I'm going to take, about a minute or so with my standard deviation, which you guys just found in part C, to go up 3 of them and down 3 of them from 22.05. So the first one's going to be 25.94. Next one is 29.83. And finally, all the way up 3 standard deviations is 33.72. Now this question really is asking about going the other direction. Okay, so now I'm going to start at the mean, 22.05, and subtract standard deviations. All right, so when you guys get those numbers, just have a quick discussion about something that we did in semester one. Okay? So in semester one, we had a rule about normal models that said 68% of the data values will fall between one standard deviation above and below. 95% of the values will fall between two standard deviations above and below. And 99.7% of the data values will be between three standard deviations above and below. So to be unusual, which is what this question is talking about, for LeBron James to have made an unusual amount of three-pointers, his number needs to be passed, right, on the left and past this number on the right. Okay, so what would be unusual on the low side? What would be unusual over here? Anything what? Below 10, right? So really unusual if below 10. Now, what would be unusual? An unusual number of, like a high number of makes for that playoffs. Unusual would be if over 33, 33, 34, something like that, right? So if LeBron James ends up making, close to half of his 73 pointers, that would be unusual, right? In a good way for LeBron. And it would be unusual in a negative way if he made below 10, okay? Now look at the question in part D. It says he made 18 of them, right? He made 18. It says the media criticized him for not hitting his usual standards of that 31.5%. Would you consider his 18 to be unusual? No, because we said he had to make below 10 to be unusually bad or above 34 to be unusually good. All right, so his 18, and if you look at our little sketch, 18 is just past one standard deviation below. Right? He's only about one standard deviation below the mean. That is not unusual. Being one standard deviation from the mean, not unusual. Okay? So I'm going to write 18 three-pointers made is about one standard deviation from the mean, which is not unusual. If you wanted to write more, you could say, to be unusual, LeBron would have needed to make fewer than 10, right? Or to be unusually good, he would need to have made around 34 or over 34. All right, so that kind of finishes everything I wanted to chat about in chapter 17.